Hello everyone, my name is Wu Xiang from Shanghai Jianqiao University, and I'm a PhD researcher. Today, I'm excited to share with you a topic that I am passionate about: effect of laser energy density on microstructure and the critical current of YGBCO and HGBCO films fabricated by PRD. My presentation will be divided into four parts: introduction, experiments, discussion, and conclusion. Next, we begin the first part of our discussion on temperature, high temperature superconducting taps. These taps are essential for various advanced applications due to their ability to conduct electricity without resistance at relative high temperatures. High temperature superconducting taps are categorized into two generations: the first generation and the second generation. The first generation of high-temperature superconducting tap is primarily composed of D-series materials, such as BESCO. The production of these taps requires a substantial amount of silver, which significantly drives up cost. Additionally, the performance of the first generation superconducting taps in terms of critical mechanical fields and critical currents is relatively low compared to their successors. These limitations have driven the search for more efficient and cost-effective alternatives. In contrast, the second generation of high-temperature superconducting tap predominantly utilized E-series materials, such as YGBCO. These materials are noted for their superior properties, including higher critical magnetic fields and critical currents. These enhanced properties make the second generation taps more suitable for demanding applications in areas like power transmission, mechanical resistance imaging, and particle accelerators. My research focused on the second generation high temperature superconducting tap due to its superior performance and potential for wider application. The fundamental structure of the second generation superconducting tap consists of several layers: substrate, buffer layer, superconducting layer, and a protective layer. The buffer layer itself includes the seed layer, barrier layer, and cap layer, each contributing to the overall performance and stability of the tap. The production process of the substrate for the second generation superconducting tap is primarily divided into two methods: IBAT technology, which is based on stainless stainless steel, offers better mechanical properties. Consequently, my research leverages the IBAT technique to develop the substrate for the superconducting tap. In our experiments, we employ PLD, which is pulsed laser deposition technology, to fabricate the superconducting layer. Especially, we prepare YGBCO and HGBCO by varying the energy densities during the deposition process. By comparing the microstructures and the electrical properties of these materials, we aim to identify the optimal processes and materials for the production of long superconducting taps. Our goal is to enhance the efficiency, performance, and scalability of second generation high temperature superconducting taps for practical and industrial applications. Through XRD pattern, such as the theta to theta pattern and in-plane and out-of-plane values, we found that this is little disorientation and impurities in the sample, reflecting good structure achieved by the pulsed laser deposition method. And HGBCO samples are much better in terms of texture values, both in plane and out of plane. And from the test results of AFM and SEM, we also can find HGBCO film exhibited better structure, surface morphology, and conducting quality than YGBCO films. Also, through the measurement of electrical properties, including the critical current and the critical current changes with the magnetic fields, we can find that the relationship profile between laser energy density and current is U-shaped, and the targets with doping element of similar atom size to substituted atom would be helpful to optimize the property of thin film. So we can find that the HGBCO film is better than the YGBCO film, and the energy density is 439. Based on the optimized technology and materials, we prepared 510 meters second generation high temperature connecting taps, and the average current of the tap is 350 ampere, and the critical current density is 3.9 MA per centimeter square. Also, the long tap from the test of the long tap, the surface is also smooth, and, and we can continue to increase the thickness of the HGBCO film, and we can get higher critical current. So, uh, thanks again for the Science Father conference again.